So the second one I would like to look at is C epsilon 2, okay, C epsilon 2. So now where does this C epsilon 2 come in the equation? Does it come in K model or epsilon model equation? Epsilon model equation, right? So obviously you already got the clue. You need to pick up a flow and a zone so that other terms become negligible and this particular term becomes dominant. So where does the C epsilon 2 occur? Within the epsilon model equation, dissipation rate, correct? So we need to consider a flow where dissipation rate term is dominant in the flow and other terms are negligible. So what kind of flow is that? So there is something called grid decaying turbulence flows, okay. There is a flow, a turbulent flow which is completely decaying, and I did mention in one of the classes that if you stop supplying energy to a turbulent flow, it will decay, okay. So you need to consider a flow where production rate is 0 and the turbulence is only decaying, and this occurs in, let's say, if you have gone and visited a wind tunnel, right, if you turn off the blower, there is a grid generating turbulence in every wind tunnel, okay. We have wind tunnels, you can go and visit in our own lab. So there will be a grid, essentially a mesh, and then an all coming flow passes through that, generating turbulence downstream. So if you turn off the blower, turbulence will decay. So we consider such a flow, okay. So here we consider grid decaying turbulence, okay. So in that, of course, we look at far downstream of the grid, in the far downstream zone. This, if you have a mesh, as I mentioned, some grid is there, and then the flow, you have an oncoming flow passing through this, generating turbulence, and then it's eventually dying. So I'm going in that far downstream zone of a grid generated turbulence, okay. So if I take such a region far downstream of a grid generating or grid decaying turbulence, so at that particular location far downstream, your velocity will be nearly constant, right. Your streamwise velocity will eventually attain the free stream velocity, whatever the background flow is, and other two velocity components are 0 there. So in that zone, what happens is essentially your ui bar is constant, okay. So the other two will be 0, the u2 bar, u3 bar, u1 bar is essentially achieved some u infinity or free stream, whatever value downstream, okay. So constant, which implying that would have come to, that is your u bar, let's say, is basically u infinity, and the v bar, w bar are 0. That's what I mean by it has come to a constant at the far downstream location, far downstream of a grid. So when this occurs, when your mean velocity is constant, what will happen to its gradient? Dou ui bar by dou xj, the gradient term, what will happen to this? 0, right. Your mean velocity is constant, so the gradient is 0. When gradient is 0, what happens to your production rates? Your production rates, if you look at the K model and epsilon model equation, is essentially relying on a mean strain rate, right. So we related the Raynaud stresses to strain using Boussinesq, and that is omnipresent in the K epsilon model. Everywhere we go, mean strain rate is present, right. So when this is 0, dou I bar by dou xj equal to 0, or the strain rate is 0, this gives basically your Pk the model, I'm only looking at the model equation, not the exact. So the Pk will be 0, P epsilon will obviously be 0 because P epsilon is a function of Pk only, okay. So Pk goes to 0, P epsilon goes to 0, and we also, let's say, neglect the diffusion terms here, very small. Diffusion terms diffusion terms are also small, so it is omitted, where in this particular zone, far downstream zone of a grid decaying turbulence, okay, not in a zone where turbulence is present, generation, right. So we are, for C epsilon 2 to get it, we are taking that kind of a flow, but for C mu we took a turbulent boundary layer, a logarithmic zone, where Pk and epsilon are balancing to each other. Here Pk is 0 completely, so you have taken such a flow, diffusion terms are gone. So if this is there, then what will happen to the K model equation? The K model equation essentially reduces to, on the left hand side, it is statistically stationary here, right, downstream here, this dou by dou t will be 0, statistically stationary, far downstream, okay. So the left hand side, dou k by dou t term is 0. There are only 3 advective terms, okay. So your u bar or u infinity is present, v bar w bar is 0 there, far downstream of a decaying turbulence. So one term survives here, that is your u bar or u infinity, I call it u infinity d epsilon, sorry dk, sorry I'm looking into dk by dx. So d by dy, d by dz terms are not present here because the other two velocities are essentially 0 when it has come to a free stream condition. So this is the only term surviving on the left hand side of your K model equation. So you are essentially looking into K decaying along x. As you walk along the flow direction, K is decaying continuously. And on the right hand side, as I said, diffusion terms are omitted, considering that they are small, production is 0, okay, right. So that means what term is surviving? Minus epsilon, sorry. So only minus epsilon survives. The entire equation comes to this form, the K model equation for this particular flow at that particular location. Similarly, epsilon model equation. Here also dou by dou t term is gone. So on the left hand side again your u infinity d epsilon by dx term survives, okay, and on the right hand side the diffusion terms are small even for the epsilon model equation, p epsilon is 0. So only the dissipation rate of epsilon term survives, which is, that's where the C epsilon 2 is there. So I would like to find out only C epsilon 2, not its friend C epsilon 1, okay. That's why we killed the friend term, C epsilon 1 is killed because P epsilon is 0, because Pk is 0 there, alright. So we have only minus C epsilon 2 epsilon square by k. If you go back and see the equation, this is what it is, the destruction rate of the dissipation rate of turbulence kinetic energy. So these two are my equations now, 1 and 2, okay. So now I am going to assume how the K is decaying along x, okay. I would like to have the turbulence kinetic energy decay as 1 over x to some power. As I walk along x, it is decaying, okay. So I consider or I can say let K, turbulence kinetic energy, decay as K equal to C x raised to minus m. M is unknown, I do not know what m is here, right, I do not know the m. Basically it is 1 over x 1 over x raised to some value. K is decaying as I walk along the x. So if I now substitute here and use your high school mathematics calculus. So if I substitute in equation 1, what will happen? I get u infinity dk by dx. Differentiating this equation here, this particular equation. Okay, so it is d by dx of c x raised to minus m equal to minus epsilon. So I get basically c minus m or minus cm u infinity, right? I get x raised to minus m minus 1 equal to minus epsilon. So this gives me basically the formula for epsilon now. Epsilon is now the way it is decaying, right? Epsilon is now decaying as c m u infinity x raised to minus m minus 1. Okay, so now I can substitute epsilon in equation 2 and differentiate that. So I get u infinity d epsilon by dx. So d by dx of cm u infinity x raised to minus m minus 1, okay, equal to minus c epsilon 2 epsilon square. So I have c square m square u infinity square, okay, x raised to minus m minus 1 whole square by k. K is also known here, which is c x raised to minus m. Okay, so if I go ahead and differentiate the left hand part, I get c m u infinity square, okay, and then I get minus m minus 1, correct. This is m minus, yes, x raised to minus m minus 1 minus 1 equal to the other side, which is minus c epsilon 2, 1 c will go away. I get c m square, the u infinity square also goes away here, right? This and sorry, I will write it here, u infinity square, u infinity square, this x raised to minus 1 whole square over x raised to minus m. This goes away and then the c also goes away here. So if I look now, it should essentially, this formula should be m of m plus 1, wait, yes, minus, okay, so this is essentially minus of minus m of m plus 1 x raised to minus m minus 2 equal to minus c epsilon 2 m square, of course, and then I have x raised to minus m minus 1 square and then x raised to m here. Okay, so if I do this, if I look into this particular form now, everywhere it is becoming this x raised to minus m minus, okay, this becomes minus 2m minus 2 and then there is m. So this essentially becomes x raised to minus m minus 2 only, this particular part, right? So this is only, so this is x raised to minus 2m minus 2 plus m. So this becomes minus m minus 2. So this cancels out. So I get essentially C epsilon 2 now is equal to just the ratio of m plus 1 by m square. Okay, m and m also I can cancel. This also I can cancel out. So I get essentially m plus 1 by m at the end. Now I can go and measure a grid decaying turbulent flow. Far downstream I can go and see what is this m, right? How is k decaying as 1 over x raised to m. So I can get m from the experimental data. What is the decay rate there? And from that I can get C epsilon. So from experimental data we know that this experimental data in a grid decaying turbulence of course gives me m equal to 1.25 plus or minus 0.06. So if I substitute it here, I get C epsilon 2 value comes out to be 1.92. So this is your another model constant. If you have used standard K epsilon somewhere, you would have seen this value. C mu is 0.09, C epsilon 2 is 1.92. Okay. This is how we have achieved 2. So we will see in the next class how the other 3 constants come out to be.